Okay, let's start it again on General Chemistry Part 20. We continue on chemical reactions and balancing chemical reaction equations. Last session, we spent time and detailed the importance, emphasized why aqueous solution as physical state in chemistry. And because most of chemical reaction occurred in aqueous solution, at least at this level as general chemistry. Alright, there are other solvents like in organic chemical reactions, and then the solvent is organic. But here we talk about most of them are in aqueous solution, water-based. And then we understand why water plays such an important role in chemical reaction, because water molecules are polar, and it has the ability to rip apart the ionic compound into cation and anion pairs, right? So that in the solvent of water, the reactants, if they both are ionic compound, they are ripped apart into cation and anion pairs. They are able to collide into each other in the solution, and then to initiate a reaction to form new compound with different definite proportion of their composition, right? So we can have some products. Then that is considered as a reaction or chemical reaction. Otherwise, we also discuss if the reactants they are able to dissociate into the solvent, into aqueous solution, but they exchange their partner or they react with each other. There's no chemical compound can be produced so that we can obtain them from the reaction. Then that is not considered as chemical reaction because there's no products. So there is no reaction occur. You just mix those chemical compound into the aqueous solution and they dissolve, they dissociate, but there's no new products generated. So that's not considered as chemical reaction. Is that clear? Okay. Now we are able to understand, then we are able to get into the classification of chemical reactions and the mechanism of reaction. What makes that reaction occur, right? We call it the driving force. So we are able to classify. Now, there are several, ways to classify. To me, I combine all these into one shot. In my handout, my writing, I classify them into about 10 different types. But also I mentioned in my handout, I said they are most of them are mutually reclassified or mutually classified into each other's group, because depends on the products or the process or the mechanism, right? So here, let's see if we are able to put them all into one shot and then get over with. The first type is the simplest one we call single replacement. Some book called single displacement reaction. Now what is the definition for that reaction is one element, most of the metal, right? In one of the reactants, if it's a binary compound or a polyatomic compound, right? There's metal in there as the cation, right? Is replaced by another elemental reactant. That reactant must be an elemental, which most of the cases are metal, right? Solid metal. And then to form a new elemental products or to form a new elemental and compound products, right? So in general form, it is one reactant as A, but just A is a symbol for any type of elements in the periodic table. And another one is binary compound composed of two elements, one is B, one is C, which is also symbolized, right? But then the A as an elemental or the metal substances is able to replace B in the compound to replace B out as a new elemental product, and then A combined with C to form a new compound as the second product. All right. So this kind of reaction, what's the driving force? The driving force, normally the book barely mentioned that. One of the book, Peter Atkins, wrote very clearly and this table attached to it is called metal activity series. So by listing more than a dozen different metals, and then the top will be the metal with the strongest replacing ability, and the bottom element will have the least strength of replacing ability, and then the top one of any can replace any elements under on the list. So we call it the metal activity series, or go by the reducing power. Reducing. We already did, right? We did already spend time to discuss what's reduction, oxidation, and who is losing electron will be what? Oxidized, right? But you are losing electron to reduce somebody else, so you become a reducing agent. Remember that? To the contrary, who gain electron will be reduced, but you pull somebody's electron into your atom or your environment, right, nearby, and somebody lose electron, so you oxidize somebody, you are reduced, you become an oxidizing agent. Now here we talk about reducing power, reducing strength. So if you are able to reduce somebody, right, give away your electron, and then get some other elements out of the compound, become a elemental products. That is the reaction we call single displacement. So what is the example here? Zinc metal replaces the hydrogen atoms, right? In what? In the HCl. All right. In this case, given the chemical reaction is the zinc metal is solid. The physical say solid. What's the oxidation state for zinc metal? As we mentioned, oxidation state. I probably did not mention very clearly on the elemental substances, because they are considered as zero oxidation state, or if they are into a diatomic molecules, either one of those atoms from the same elements will be considered having a zero value oxidation states. All right, and zinc as a elemental substances is a metal and considered a zero oxidation state. Now the hydrogen and the chlorine in hydrochloric acid aqueous solution, we're not there with a strong concentrated acid, we're there with aqueous solution, and then the hydrogen, as usual, hydrogen represent, right, or present a +1 oxidation state, and the chlorine is -1, right? Now, replace hydrogen out of the hydrochloric acid, and the two hydrogen atoms combine into a diatomic molecule hydrogen gas, and it becomes zero, but inside the +1, and it becomes zero as diatomic molecule. Who's the electron the hydrogen taken from? Taken from zinc. Zinc from zero oxidation state become 2+ oxidation state by what? By going from zero on the number line, the left to the right, is what? It's being oxidized. Right, oxidized. And it's being oxidized, so it becomes a reducing agent. So zinc is stronger reducing agent than hydrogen in the metal activity series. You say, well, metal, and zinc is metal, I understand the transition metal. But what about hydrogen? Hydrogen is not metal. Well, I already mentioned in one of those parts, I said hydrogen is metal, right? If you can go down Jupiter, and then the hydrogen gas, right, under the thick, right, 30-some thousand miles thick atmosphere, and actually hydrogen gas was compressed and then into liquid, and then when temperature goes very low to -269 degrees Celsius, almost 3 or 4 Kelvin, the hydrogen gas or hydrogen molecule or hydrogen atom, they combine cross into solid, and then it does have a metallic sound, but you cannot hear that because that's not the environment you are able to go there, right? Hydrogen does, and also on the periodic table, hydrogen, where located hydrogen? Hydrogen right on top of what? Alkali metal, the first one, am I right? So it is metal. So, but in the reducing strengths, hydrogen weaker than the zinc, so the zinc is able to reduce hydrogen in the hydrochloric acid, giving 2 electrons to the hydrogen. Each one of hydrogen atom gain 1 electron. Gain electron is being reduced. The hydrogen become a oxidizing agent. Oxidizing who? Hydrogen oxidizing zinc. So zinc from 0 become +1. Right? On the number line from 0 plus 1, 2 plus 1 is from left to the right. It's oxidizing direction. On the other end is reducing direction, because reducing is just the number getting smaller or decreasing. Right? So that's what we already discussed in the past. So hydrogen become single out, right? Become a hydrogen diatomic molecule, and it's a gas. So in the solution, right? Aqueous solution. Then the gas can hydrogen gas stay in the aqueous solution? Yes, very limited amount of hydrogen gas will stay in the aqueous solution, which this time is going to be zinc chloride, right? Because zinc is going to combine the chlorine to form zinc chloride. The zinc is 2 plus 2. The chlorine is 1 minus, so you got to have what? We try to make a compound, go by the oxidation state, the value, right? 1 plus 2 require 1 or total -2. So, but the chlorine only offer -1. So you got to have 2 chlorine atom. Each one what? Each one is -1, right? So you get -2. So balance this charge and neutralize as a neutral compound, binary compound. Even we got about 3 atoms for the zinc chloride, like the Cl2 outside. So what is the physical state? Because this compound is an ionic compound, and then it will be dissociated. We just discussed, right? Now you hear the term dissociation, dissociated, and aqueous solution all the time. Now you go back to part 19 or part 18. You say, oh my God, this Peter Chang gives all these baloney. We know this, polar molecule and aqueous solution. Why you spend so much time on? Now you know why I spend so much time on. Because you need to be very careful, very clear. You have to have a clear head on what kind of physical state and what kind of solution you deal with. And then we just started. We're not even get there. We're going to get into the part you're going to have to use the knowledge you learn on dissociation, ionization, and cation, anion, aqueous solution. They're charged all the time when we reach the redox reaction and writing ionic chemical reaction equation or net ionic chemical reaction equation. Then you cannot live without this knowledge. Alright, so that's one of these products. So the driving force, right, is this, and then in this particular case, what is driving force is produce gas or solid. We've got another example for solid. And also the electron transfer is driving force because of redox. So this reaction called single replacement reaction can also be classified as another type. We call it what? Gas formation. What is gas formation? Hydrogen gas. The arrow point up means what? Evolve, bubbles out. Very small amounts will be dissolved into aqueous solution, water-based, right? But if you heat up, all the water start boiling, and then all the gas will be expelled, right? But it will not stay in the water because of what? Hydrogen gas or any kind of gas, right? Has a lower density, right? It's less dense than the liquid, so it won't stay in the liquid, but go what? Ascend to the atmosphere, right? So leave out of the aqueous solution. So this hydrogen gas, we have to spend time to detail it. The hydrogen gas, as a product, you have to collect it over the beaker, and then it tells us why this reaction is only one direction. It's irreversible. Why is not reversible? Well, how can this hydrogen gas bubble out of the solution and then automatically spontaneously go back to the solution, dissolve and go back this way? There's no way to do that, right? So it's going to go one way, and you cannot force it back. If you force it back, you still don't put arrow this way, because this arrow means what? The spontaneous direction of the reaction occurs, right? Not under any force. Then that is not spontaneous. Spontaneous means automatically, by itself. It happens no matter what, correct? Now here, so this arrow is a single arrow. single arrow, single direction arrow, and it's not reversible because why? Because hydrogen gas bubbles out the solution chamber, which is the reaction chamber, no longer in there to react with those, to go backwards, right? But this compound, iron compound, will completely, it's electrolyte, and it's strong electrolyte, and it will completely dissociate into what? If 1 unit of zinc chloride would dissociate into what? 3 entities. 1 zinc cation, 2 plus charge, aqueous position. 2 chloride, right? 2 chloride anion, right? 2 right here, subscript. What is physical state? Also aqueous. So this one become 3 entities, 2 identical and 1 different zinc. So that is the whole thing, right? That's the whole thing. Understand that? Now this can be considered as a gas produced. Now I'll give you another example. Is the solid produced or solid formation reaction. Another example. This is not my handwriting. That's terrible handwriting. Gosh. All right. So here, let's see. Now. The copper, all right, metal, right, replace silver in nitrate. Now, in nitrate means what? Nitrate NO3, right? Why? See. Silver in nitrate, same thing as silver nitrate, because we replace the silver metal out of nitrate. What is nitrate? Silver nitrate. So what is this reaction? So the copper will be metal. So copper here, Cu, right? 29. It's the third period of transition metal on the right hand, and then the zinc is the 30, right? And then 29 is right before the zinc. Copper is solid, right? Solid. You know copper. Copper wire, copper very expensive, right? As we know, currently copper is a hot commodity, right? And then people stealing people's house were stripped by the copper wire. People selling the scrap copper wire. Where do they go? I heard they go to China. Oh, my God. So copper react with what? React with silver. What is silver? Ag, right? Silver, Ag, right? Ag is what? Nitrate. Now, do we have any parentheses? No, we do not, because we already mentioned silver, right, has only 1 oxidation state, which is positive 1. Positive 1, right? And copper can have +2 and +1. But here is metal, so the oxidation state for copper is 0, right? For silver is +1. For nitrogen is what? Nitrogen, the nitrate must be -1 because the whole thing, NO3, is a polyatomic cluster we call polyatomic anion, right? We discussed all these a long time ago, right? A couple of weeks ago, around part 8, part 9, or part 7. And then if you miss those, go watch my clips or go read the book. I think the table, hope not many mistakes down there, on OpenText, right? The book you can access online, and then check out the polyatomic anion list, right? Table. And then the NO3 shouldn't be 1- as the charge of anion, but if it's a 1- outside, we all know oxygen is what? Oxygen 99.9%, right? Present itself as a plus or minus, a -2, right? -2 oxidation state. The 3 of them total is a -6. The -6, the whole thing become -1, so the nitrogen must be what? +5. We already done this exercise in my homeworks, right? At least two homework involved oxidation state. So this one is +5 for nitrogen, and this oxygen is -2. Now you see why I spend so much time on those concepts. Oxidation states, electronegativities series, right? And in the past, we already talked about other number line related, right, series of different concepts. Now here plays a role. So what is the physical state? Silver nitrate is a very, very strong electrolyte, and it is ionic compound, and then you will form a cation and anion pair. But anion pair, anion are the nitrate. Nitrate, it does not go apart. Nitrogen and 3 oxygen separate. No, they stuck together in most of chemical reactions. Just remember this way. All right, they don't split. So you will have a silver 1 plus and the nitrate 1 minus, right? The whole thing 1 minus, right? So that is so, but it's aqueous. Only aqueous means the ionic compound can be dissociated, right? You heard dissociate again. Now the reaction is going to be one way. Why? The copper has a stronger replacing power or reduction strength, right? Reducing strength, right? To reduce the silver, to give its electron into the silver, so the plus 1 silver becomes 0 out as some elemental products by itself. Now that's a process. If you have something, involve this kind of reaction, you do what? Which one's more expensive? Is the silver more expensive or copper more expensive? Of course, silver, right? Silver is slightly more expensive than copper. Oh, maybe I'm wrong. Copper may be more expensive right now. I don't know, right? Because the electronic age, we need a lot of copper, all right? Electron circuitry. But silver normally is more expensive. So if you have a lot of waste from industrialized waste, right, downstream, you know there's a lot of silver. Oh, that's what I did. My father did. And he actually recovered all these silver, gold, and the platinums, all these precious metals from what? From the electroplating trash, the plating solutions. Before it dumped into the river, he cleaned everything. All right, every bit of metal he picked them out chemically in the chemical process, and don't go into the environment, the early environment. That was back in China. He brought so many pans of silver powder, and then my mother brought over here in this country and passed the LAX airport in Los Angeles, and the alarm went off. So they checked my mother's luggage, find bottles of silver powder. So no, you cannot bring in. So we'll have to bring back. So that is something happened. But we still have those chopsticks made. The silver my father recovered. Anyway, silver, you want a silver. So you do this reaction to replace the silver out of nitrate, and then you spend some less money for using copper, right? So what happened? The silver will come out as solid. Now, if as solid as metal, the oxidation state for elemental substances or elemental molecules become 0. So the oxidation state for silver metal is 0, right? And then replace the copper, replace silver, the copper will combine with the nitrate, become copper cupric, because copper this time 2 plus, copper nitrate. Ooh, let me. Now nitrate we know is -1. Copper is what? Copper is +2. So +2, in order to achieve neutrality for the ionic compound, the nitrate, 1 nitrate is not enough, because 1 minus cannot balance 2 plus. So you got to have doubled 2 outside. That is the parenthesis. My parenthesis goes too straight. Right? This 3 is inside. This 3 is inside. This 2 is outside. That clear? All right. So now you have 1 minus and then time 2. 2 times. Right? 2 times. So now you neutralize. Now, is that balanced, the chemical reaction? It doesn't seem to be. Why? Why is not? In that this one got 2 nitrate, this one got only 1. So what happened? So we have to double the quantity of the silver nitrate into 2, right? You have 2. So now you have 2 silver nitrate. Got here, nitrates are 2. Oh no, silver got 2, but here only 1. That's okay. We done with this also. So 2 nitrate. Now let's check again. Is that balanced? Now we have 1 copper, 2 silver, right? 2 nitrate, 2 silver, 2 nitrate. Yes, they're balanced, right? The mass are balanced. You count number of atoms means what? Each atom of different elements will have a different amount of mass according to their what? Atomic mass units, right? And then, so you have 1 copper was a 63.48, right? AMU each, that's a 63.4. The same thing, silver is 107, 2 of them with 214, 214. They're all mass balance. What is charge balance? Of course, it's 0, this is 0, this is 0, this is 0, right? They're all neutral compound. But what is physical state here? So this physical state is going to be AQ, right? Aqueous solution. This is going to be solid. Solid what? Solid is going to be precipitate. Solids are heavy, right? Most of solids are heavy, especially metals, right? So in this case, solid heavy go down to the bottom of the reaction beaker, right? So you normally, currently, no textbook will use those symbols, but I love those symbols. Give you a visualization of what happened inside a beaker. Now people, nowadays, chemistry teacher, chemistry students, they learn something on the paper, on the book, and they don't even remember. Why? Because they cannot imagine what actually happened inside a beaker until they do reaction in the chemistry lab. But then, if you're not pointing that out, they not even think about it. They still go, oh, this is the book says 2 Ag, that's 2 Ag, that's 3. But still, you should, if you learn chemistry, right? Chemistry, people say it's a tough subject. No, I don't believe so. And depends on who teaches you, right? But you also have to have a personal vendetta, personal try to understand this process, what is going to form, even that's invisible, right? Try to imagine. Close your eye, imagine. In this case, copper, right, replace the silver out of nitrate, silver become a single solid, and solid is heavy going down the bottom beaker. Not like a gas going up, right here, arrow up, right? I like those symbols, arrow up, right? Hydrogen gas is much heavy, hydrogen gas is much less heavier and bubbles out, and the silver is heavy, so this is single displacement. One, replace one of them, right? And then this come out, and this replace combined with the nitrate, become new products, right? So the elemental, new elemental, compound, new compound, right? The reactants and the products. The reaction is one way. Why? You cannot redissolve. No. Put it this way. The silver metal at the bottom of the beaker, out of the solution, after reaction is completed, it will not spontaneously dissolve itself back to the solution with silver nitrate and then go backwards to copper being, isolated by itself, and the silver nitrate become one of the product going backwards. Because what? Because the metal activity series, the copper is stronger than the silver. Copper, for the reducing power, the strength is stronger than the silver. The silver will be reduced by copper. Copper will replace the silver. So how many electrons? The copper become 2 plus, right? 2 plus. So there's 2 electrons. Also, 2 electrons, right? 2 electrons goes from the elemental copper goes to who? Goes to the silver in 2 molecules or 2 formula units of silver nitrate. Replace both silver with more electron, and then reduce the silver plus 1 into silver 0, and then become metallic silver come out of the reaction. That is redox. So it can be reclassified, right, as solid formation as well as redox. Now that's clear. Time's up. All right.